An old friend, Jeff Van Cleve. I'll say a few words about Jeff. Jeff is physicist by training. He did his undergraduate at Princeton in physics, and then he decided to go back to the old world. So he spent a year in Cambridge being trained in condensed matter physics experiment. And then he came back to the US, where he did his PhD at Cornell, working again in low temperature physics, helium-3 and helium-4 type of experiments. And at some point he thought that physics was not as exciting. And he was fortunate to actually be next to the astronomy department, where the project, the PI of the Spitz area infrared spectrograph, Jim Houck, who was also trained as a physicist 20, 30 years before him, appreciated his qualities, and he made him an offer that he could not refuse. That was to work on the infrared spectrograph from Spitzer, and that started sometime in the early 90s and continued up until for probably 15, 20 years, because there was
like 3 years ago. It's like forever.
so then Jeff moved to Ball Aerospace and NASA Ames, and then back to Ball Aerospace. And he has done, he worked for the Kepler mission, he worked for Sophia, and since he did extremely well, he managed to get an early retirement recently and visit the really old Europe. So he came to Greece, to Athens and Santorini, and now this past week he's with us in Crete. And one thing I should mention is that in addition to being an extremely good person with the instruments, Jeff is very imaginative and also, how to put it, he had an entrepreneurial spirit. He actually created a company. I have the logo, but I didn't have it with me, back some 20 years ago, to propose a mission to go and explore and get helium from the outer planets of our solar system. And NASA hasn't been convinced yet, but Jeff will talk to us about this and other projects that he has worked over the past few years. Thank you, Jeff.
Thank you, Vasilis. And then we started working together in 1999, was it? When he was on Spitzer Space Telescope, and we just kind of hit it off. And we talked about me giving this lecture 5 years ago, and then COVID got in the way, but then here I am. So
sorry, I was
Kalispera, Evkaristo, Mila, Liga Elenica, but I will speak in English so you understand that. Okay, so my talk is what you would call science fiction. It's based on science in terms of the composition of the outer planets, and it's fiction because no one has built a working fusion rocket. But since I'm retired, I don't have to report to a boss about the financial payoff of my research. So this project I started 23 years ago when I was at Ball Aerospace, but for years and years, I let it rest. And now that I'm retired, I've returned to it. There actually was a time when Ball would pay me to do this stuff, but those days are long gone. So what I'm going to talk about here is mining the outer planets for helium-3 to burn in imaginary fusion reactors and rockets. And that seems like really far-fetched. It's like 100 years from now. But I call myself the chief evangelist of my company, Interplanetary Sales and Marketing, because I think it's important for human beings to believe in an optimistic vision of our future instead of gloom and doom. That just like Elon Musk dreams about colonizing Mars, my dream here is that we will mine these planets for starship fuel and eventually go out to the nearby stars. So in particular, I wanted to thank you all. I know mostly you do objects of non-negligible redshift. So I'm talking about objects of zero redshift. So I appreciate being invited here today, because that's probably outside the wheelhouse of most of you. And then these pictures are of Saturn. with the Cassini mission coming to an end, but providing proof that one can pass through the innermost rings of Saturn multiple times. And then this is an image in the 2-micron band of Uranus from the Keck Observatory showing storms and their innermost rings. So even though this vision is over 100 years from now, there's things we can do in our own time to go down that road. It's kind of like the Drake equation. Like, we don't know how much extraterrestrial intelligence is out there, but in my own time, I worked on Kepler that quantified the average number of Earth-like planets around each star. So just like Drake equation, we approach this goal step by step with things that we can do now instead of the indefinite future. So the long-term vision is extracting helium-3 from either the moon or the outer planets. An early vision was Project Daedalus from the 1970s. So just for scale, this is like a 450-ton payload, which nowadays seems crazy because everything's gotten smaller and smaller. So this is an early vision, but kind of obsolete. And then with my collaborator Michel Lamontagne in Quebec, come up with some more recent visions of a helium-3 powered starship. But we'll all be dead by the time this happens. So the question is, what can we do now as astronomers and astrophysicists that has meaning in the context of this vision? And it turns out that we have our budget problems in the United States, but the next big flagship mission, as they call it at NASA, is to Uranus. He taught me how to pronounce the planet's name correctly. And then there's a Chinese mission called Tianwen-5 that will also collect important data 2040, 2050. You know, as astrophysicists, we're used to talking about missions 20 years from now. So this doesn't seem completely insane to me to be talking about that. Plus, there are ground-based and JWST observations that can make contributions in the next 2 or 3 years. So we can do things now that has meaning within the context of this vision. So the scope of this paper is to talk about helium-3 mined from Saturn or Uranus. There's also helium-3 on the moon, but as shown in this picture here, but that will run out in about only 100 years. The purpose of helium-3 on the moon, which the Chinese are looking for now, is to jumpstart a helium-3 economy. So when we run out of helium-3 on the moon, we'll be highly motivated to find it on the outer planets. I've also presented some papers about how to design balloons in the atmospheres of Saturn and Uranus. I put that in other papers just to keep this down to a reasonable length. And I'm not going to tell you how to build a fusion reactor. People have been working on that for quite some time, and I don't want to take up your time today with that. But I'm going to lay out the part of this vision that involves the astrodynamics of recovering material from the atmospheres of Saturn and Uranus, and either getting it back to Earth or generating Starship fuel on the spot. So the way this paper is laid out, I'll introduce some concepts common to both planets and talk about them specifically after that. So this is a PowerPoint level engineering diagram from Hein et al. In 2010. And so the concept, and this is very conceptual, there's just like PowerPoint figures here, is that you have a balloon in the atmosphere of Saturn or Uranus, and it has a mining platform that distills the helium-3 isotope from the atmosphere, ascends from the atmosphere with its payload to a transfer vehicle, which then returns to Earth to generate clean fusion power. And then the cycle repeats itself with more factories being built and aeroshells for descent. So it's possible to generate electricity on Earth And the reason we like helium-3 deuterium fusion is because if you burn deuterium and tritium, first of all, you have to make tritium. And second of all, 3/4 of the energy is released as neutrons, which you can't steer with electromagnetic fields. So they all impact the wall of your reactor and embrittle the chamber, and you can't use it for a rocket because the neutrons go out in all directions and can't be shaped into a thrust by a nozzle. While with the helium-3 deuterium, all the products of that reaction are charged and then can be focused into a rocket thrust. So what would a mining aerostat look like? This is from my colleague Michel Lamontagne in Quebec. He's not only interested in helium-3 fusion, but he has really nice rendering skills. So he made this picture, which is on his website here, which is mostly in French for people who read French. And so this is a hot air balloon. So there's hot hydrogen inside that of course weighs less than cold hydrogen. And there's a nuclear powered thermal rocket down here. And then the precious helium-3 payload is up at the tip of the rocket. So there's an artistic view of it, and this is more an engineering view. It's about 70 meters across. There's a nuclear reactor, of course, and a plant that extracts not only helium, but the helium-3 isotope from the atmosphere, storage tanks, and a shuttle rocket to bring it out into space, either for Starship fuel or to send to Earth to generate electricity there. So where would such a thing be? Well, based on the geography of each planet, you want it to be close to the equator of a planet, so you can make good use of the rotational velocity of the planet to return stuff to orbit, but not so close to the equator that you're rising up directly into the rings and you might hit some things. So I've kind of started some work optimizing that, but it's roughly a 3 to 7 degree inclination. And then if it's too high in the atmosphere, there isn't enough lift in terms of kilograms per cubic meter to make a balloon fly. And if it's too low, then it's really hard to get out of the atmosphere with your payload or communicate outside the atmosphere. So between the 1 and 10 bar level on Saturn, you have ammonia and ammonia sulfide clouds, and on Uranus, you have methane and hydrogen sulfide clouds. And so the balloon would bob around in between these levels here and begin extracting helium. So throughout the history of lighter than air vehicles, wind shear and storms have been a big problem. So this is the from the age of Zeppelins. Here's the R101 from the British. Well, that crashed because of a storm. The USS Macon, that crashed because of a storm. And these things are really susceptible to weather because they have a very high area to mass ratio. And balloons are even worse because they're not propulsive and you can't steer them around weather. So in terms of science we might want to do, we would like to examine what is wind shear on the length scale of a balloon. How much turbulence is there that will move the balloon around and possibly destroy it, like you see here. For a terrestrial aircraft, it's measured, wind shear is measured with Doppler radar or LiDAR, but in order to get a signal, you need some kind of particle to scatter off, and it doesn't work in clear air. However, fortunately, those cloud decks I just mentioned to you before would scatter particles, and then you would be able to measure wind shear in storms. And this is something we want to do before investing money to actually build such a factory. But again, in the next 20 years, 30 years, measuring wind shear in the atmosphere of Saturn and Uranus would be a science topic that is both interesting in its own right and would contribute to this helium-3 vision. So looking at the SpaceX Starship, the return vehicle that would return the helium-3 to space, ultimately to the Earth, would look a lot like SpaceX Starship. Now, this didn't work, the first or second time, but Elon believes in test, fail, learn, test again. So I think we're going to learn a lot from something like this. And what's important is this is a high atmospheric entry vehicle that's meant to be reusable. And so I think once they get that right, it's going to tell us about how to build the shuttle that will return the helium-3 to the Earth. So the shuttle uses a nuclear reactor to heat hydrogen as hot as possible without melting the reactor. And then because smaller molecules have faster speeds at a given temperature, you can get an exhaust velocity of 9.5 kilometers per second. So that is enough that a single stage vehicle could rise from the atmosphere of Saturn or Uranus to deliver its payload of helium-3 to space. But it's a large vehicle and hydrogen has low density, and so there's a bit of a trade-off there. But when you look at something like Starship or the space shuttle hydrogen tanks, you want to have roughly 6 units of fuel for every unit of payload to have enough mass to keep the vehicle from falling apart. And it turns out that then that gives you a total change in velocity of about 18 kilometers per second. So with the rotation of the planet, that's enough to get you into a near orbit around either Saturn or Uranus. So again, Michel, with his great artwork skills, has rendered a design for a transportation ship that would take the airborne factories, the balloons, inside these aeroshells that would then break against the atmosphere. And then these engines here would carry this out from Earth to the vicinity of Saturn and Uranus. So, of course, like almost anything, it's powered by a nuclear reactor with cooling fins down here. It carries 2 propellant production units. So each of these shells contains a balloon and a helium-3 factory, as I showed you in an earlier slide. And these are delivered into the atmosphere. So now to some specific things about Saturn. This is what the geography of Saturn looks like. These are various rings of Saturn. And then this little balloon-shaped symbol here is where our aerostat mining facility is, down in the atmosphere. And then we have enough energy to lift the helium-3 payload to what I call the D- station, which is just under the D ring. And since you burn helium-3 with deuterium, the rings themselves would provide some water and therefore deuterium. I don't think we know the deuterium to hydrogen ratio in the rings of Saturn, but that's an example of science we might do in the next 20 or 30 years. And so we could bring the helium-3 out from the atmosphere to a low orbit just below the D ring, transfer it to a high orbit just above the F ring. And then once we're clear of all the ice and debris in the rings, we could take a very low thrust but high specific impulse engine that would carry the payload back to Earth. We don't want to use a low thrust engine deep in these rings because by the time we built up enough thrust, we'd have probably hit something in the middle of the rings. The biggest thing that happened since I started this research in 2021 is that JPL's Cassini mission had an extended phase called the grand finale. And long ago, people were afraid of crossing the asteroid belt because we'd like run into things and blow up. And that didn't happen. We sent the Voyagers and Pioneers out there, and no one ran into an asteroid, but people were afraid that would happen. And so now, back in 2005, when I was last doing this, no one wanted to look at Saturn as a source of helium-3 because you couldn't get out of there without running into the rings. But then Cassini, after they had finished their primary mission, actually passed just outside the F ring on these orbits, and then used a Titan gravity assist to pass inside the D ring, and it did it like 16 times. So that's like proof that you can rise out of the atmosphere of Saturn with a space vehicle, go into a high orbit, and not run into anything. So we could talk till we're blue in the face about analysis, but Cassini actually did that. And so that has made Saturn a much more viable planet for helium-3 extraction than it looked 20 years ago. So this is great news and made me a lot more interested in Saturn. So the transportation nodes in the Saturn system, like how do we move things from one place to another? If you look at the amount of velocity change available, we can't rise entirely into deep space from the atmosphere. But as I showed on the previous picture, you could go to a station just below the D ring and then transfer payloads just above the F ring, and then mine water ice for reaction mass from the rings themselves. So this would not be for burning and fusion. That wouldn't be deuterium, helium-3. That could be part of it. But for a nuclear thermal engine, you would just want normal hydrogen to use as reaction mass, and you could extract that from the water in the rings. And so the scheme is a two-step process where you rise out of the atmosphere to just below the D ring, transfer your precious helium-3 payload to just above the F ring, and your reaction mass for that transfer is taken from the rings themselves. So maybe environmentalists will complain that we're disfiguring the rings of Saturn to extract these hydrogen resources, but I'll leave that for another day. So what's happening in our own time? Well, the European Union has a mission called Hera, which is a Saturn entry probe, kind of like the Galileo mission. People have tried to figure out how much helium there is on Saturn and have gotten greatly different results because, as you know, helium has no dipole moment. And so the only way to measure helium is by making a model that contains average molecular weight, and those models are more of an art than a science. Let me just put it that way. So you can't directly measure helium concentrations, and you cannot measure the helium-3 to helium-4 ratio just from remote sensing. So we've had Cassini, Voyager, all that. But if you look at the literature, the estimates of the amount of helium vary by a factor of 5, depending on your models, 3% to 15%. And these are all people who know what they're doing. So I would say basically, we don't know what the helium concentration is on Saturn. So we need an entry probe with a mass spectrometer to have any confidence in the results. So everyone's got budget problems, but there is a ESA mission called Hera that might result from an ESA-USA collaboration. And of course, it'll look a lot like Galileo. I mean, convergent design. And it's also a possible mission for NASA's New Frontiers medium-sized planetary mission. Again, we have our budget problems, but you know, you don't believe in this stuff, it'll never happen. So there's definitely something on the board for measuring the helium concentration and the helium-3 ratio in Saturn's atmosphere. And that's really interesting from a scientific point of view as well, because if a metallic hydrogen core is forming in Saturn, it's an interesting question as to whether the helium-3 to helium-4 ratio is enriched, because typically in solution processes, lighter isotopes have a lower solubility. So even though the helium may be sequestered in a metallic hydrogen core, the helium-3 ratio might be higher because it's a lighter isotope. I've talked to people at conferences, and people agree it's an interesting question, but nobody has an answer to offer on that. So this would be hugely interesting to get that mission going. So in addition to probing the atmosphere, we want to figure out how we can hover above the rings so that we can mine the rings for hydrogen and even deuterium, and transfer payloads from close to Saturn to the outer edge of the rings. And there was actually a project called, you guessed it, Saturn Ring Observer, led by Phil Nicholson of Cornell, Matt Tiscarino of SETI, and Linda Tom-Spilker of JPL. And they had this concept where this would just kind of hover over the rings with a certain amount of propulsive capability and be able to descend and look at individual ring particles. So this would be a prototype of a ring mining vehicle that would then provide reaction mass to the shuttles, bringing the helium-3 from close to Saturn up to deep space. More recently, one of these authors, Tiscarino, has proposed a close ring flyby, so they can look at the rings in detail, but they'll be moving at like 8 kilometers per second with respect to the rings. So in terms of learning how to keep station, hover over the rings, this is not as good, but it's a lot less expensive, and it's still progress towards understanding the detailed structure of the rings. So when I showed you all those Zeppelins that got wrecked by wind shear and storms, there's a little bit of knowledge of what weather's like on Saturn. What was really interesting recently is that these huge storms erupted at mid-latitudes on Saturn. I think this is a Cassini image, and the planet seems to store up a huge amount of energy over its 29-year cycle around the sun. And these kind of storms erupt at mid-latitudes, which might destroy a helium-3 mining aerostat. So be able to characterize storms on Saturn is, again, the kind of science that could even be done from the ground that would help us understand, like, would it be safe to have a mining aerostat at the equator, or do these storms only erupt at mid-latitudes? So there's no mission concept to measure wind shear and storms in situ, but it's an example of science that's doable. It's just not fundable at this point. So it's not like it violates a law of physics. It's just violates some laws of government funding. But storms like this are really interesting in terms of having a balloon in the atmosphere of Saturn and whether it would be destroyed by storms. So to Uranus, this is the landscape of Uranus. So similar to Saturn, we have an aerostat in the atmosphere of Uranus. And then just inside the Zeta ring, there would be a station to transfer cargo, and then take that cargo above the Epsilon ring and then out into deep space. And there's a lot less known about Uranus than Saturn, because there's only been a few hours of data from the Voyager mission 1986, instead of having an orbiter like Cassini that could watch things for, gosh, they were up there like 15 years. So we don't know whether these rings are rich enough in water to provide either deuterium or reaction mass. Maybe it's all carbon, maybe it's all graphite. We don't really know. I mean, this is reflectivity in the near infrared. So when it's imaged by James Webb, it looks like there's a lot of stuff there, but we don't know whether ice mining is possible in here. If we have to go all the way out to the moon Miranda, then that makes the transportation system a lot more difficult because you need to gather propellant here and go back and forth. And since the rocket equation is logarithmic, you wind up having a vehicle that's 10 times bigger than if you could just mine the rings of Uranus for water and deuterium. So what I just said there, that's kind of summed up here. The rocket would come up from the atmosphere, gather reaction mass from the rings, but because of the large scale height of the Uranian atmosphere, that would be about 3,000 kilometers above the level of the aerostat instead of 300 kilometers. Then at the Zeta minus station, payloads transferred to a nuclear thermal rocket tug to take it to Miranda, and it's fueled by hydrogen extracted from the rings, if that's indeed possible. So this is a great example of a scientific question: is what is the water and therefore hydrogen density of the rings of Uranus? And we don't know. We just had a few hours of data from Voyager, so that's a good guide to near-term research. And then before our most recent budget crisis in the United States, we had a Uranus mission called Orbiter and Probe. And so it has the usual stuff: magnetometers, cameras, thermal IR, and a probe to measure the structure of the atmosphere, mass spectrometer, that'll give you the helium-3, helium-4 ratio, orthoparahydrogen, which tells you a lot about atmospheric circulation. So this was like really a great idea about 2 years ago. And then we had a budget resolution, so we could give more tax breaks to billionaires, I guess. And so this is kind of receded into the future. And the problem with Uranus is, it's tilted on its side. So back in 1986, only the southern hemisphere of Uranus and the moons were illuminated. And we wanted to go back there at roughly an equinox conditions so that we could see the whole planet illuminated. Well, that would require arriving in around 2040. So as things slip by, then half the planet will be in darkness. So I don't know if that will carry any weight with Congress, but that was a good reason to make this happen now instead of 30 years from now. So JPL and APL and Johns Hopkins are working on this, but it's a little bit delayed. However, our good friends in China are actively seeking helium-3, both on the moon and in Uranus. So here's an example of a mineral returned from China's robotic sample return mission, Chang'e 5. And it's called, of course, Chang'e site. But these crystals have helium-3 embedded in them. And Fan and Jin, in a really nice paper in 2007, talked about China's strategy for mapping the moon's helium-3 reserves, which is then related to what we're talking about with Saturn or Uranus, because if you build these reactors to use lunar helium-3, that'll run out, and you're going to want to seek helium-3 at Saturn or Uranus. And so the Chinese mission is called Tianwen, and Tianwen 4 is a Uranus flyby, and Tianwen 5 is proposed to launch in 2035 and enter orbit around Uranus in 2050. So that's not a done deal. It's for consideration in China's next 5-year plan. What's really interesting about it is, unlike the US ESA mission, the Chinese mission concept includes aerostats. They're actually going to deploy balloons into the atmosphere of Uranus and gather engineering data that would be useful for helium-3 mining stations. So, some people think like helium-3 is kind of a crazy idea, but the Chinese have been publishing a goodly amount, both on the moon and looking forward to Uranus. And such an aerostat is a qualitatively more advanced step towards the helium-3 mining future. They'll actually figure out how to make something float in the atmosphere and do something while they're there. So I mention this because for our United States government. Scientific curiosity is great, but fear is a much better motivator for space missions. So maybe that will have some effect. So you could take this, you could take the Saturn ring observer concept. So we have talked about using rings for reaction mass or deuterium. And no one's actually proposed such a thing, but I've read Tom Spilker's papers. There's nothing fundamentally different about having such a ring observer for Uranus. It's just a little bit lower on the contemporary scientific priority list. But if we could learn what the rings are made of, then we could decide whether we have to go all the way to Miranda for reaction mass. And then, because you have to go two ways, winds up increasing the mass of your tug, your space tug, by a factor of 10. So this would be like hugely valuable to know whether we could mine the rings of Uranus or have to go all the way up to Miranda to gather reaction mass. And since we've never had a mission in orbit around Uranus, we don't have proof that it is safe to cross the ring planes, as demonstrated by Cassini. Again, as theorists, we can talk till we're blue in the face about the impact hazard of passing through rings, or we can just do it and see whether it survives. So even a small spacecraft that passes repeatedly through the rings to show that it is possible to do so would be a great thing. We know even less about wind shear and storms on Uranus because we only spent a few hours there in 1986. But we've been learning some good stuff from ground-based observatories. So this is Uranus with a storm seen in the K prime band. And that, I think, was by Imke de Pater, and they used the Keck telescope. And none of this was visible when Voyager went by. And so it's kind of like Saturn, where you had these big mid-latitude storms that were only seen by Cassini after the seasons had gone by. And so similarly, there are storms on Uranus that might be a hazard to aerostats and balloons in the atmosphere. And we know very little about it. And so a probe or an aerostat that had a wind shear instrument on it, for example, a LiDAR, that would bounce signals off the clouds would be very valuable. It's not the top of the science priorities, but it's an example of something that leads to the helium-3 future. So this all sounds like really far in the future, crazy stuff, but there's actually an approved James Webb proposal, which says they're going to observe the faint and dusty rings of Uranus and the Zeta ring and other material. This will provide time-critical knowledge about potential hazards to shape the planning of NASA's Uranus orbiter and probe mission. So even though this is like, whoa, far in the future, helium-3 stuff, that's happening now. That's happening in the next James Webb call for proposals. And I forget the authors of this proposals, but there it is. And so they're explicitly acknowledging the need to learn about potential ring crossing hazards, as well as the particle size distribution, which would be given to you by color information, assuming Rayleigh scattering. So even though this is like 100 years in the future, there's actually an accepted proposal now that builds towards this kind of vision. So I think that's pretty cool. So our to-do list for 2030 and say 2055. You look most of you look young, so you're probably around 2055. Just learn about the helium-3 concentrations of Saturn and Uranus from entry probes, since it's kind of a fool's errand to learn that from remote sensing, figure out how to operate close to the rings, and whether we need to design what are called Whipple shields to protect against small particle impacts, how do we operate balloons, hot hydrogen balloons in these atmospheres? It's at least a proposal for China to have aerostat operations. How much water is in the rings of Uranus? And then there isn't enough water, figure out, learn more about Miranda, which is obviously a source of water, but it's a very great distance from Uranus. And then determine the hydrogen deuterium ratio in the rings of both planets. And then finally, some kind of wind shear instrument that either has Doppler radar or LiDAR to determine the amount of storms and turbulence, so that a balloon can fly. So it's been a great year in space. A lot of countries have participated. Greece has joined the Artemis Accords for exploring the moon, which is part of the helium-3 vision. And then all these institutions have landed on the surface of the moon in the last year. Indian Space Research Organization, Japan, China, NASA. And let me conclude with a nice saying by Prime Minister Modi of India. Said, the success of Chandrayaan-3, which is their lunar lander, is not just India's alone, but belongs to all of humanity. So hopefully, geopolitics aside, we can all work together on making this vision of the helium-3 future come to pass. So I'll leave you with one of Michelle's renderings. This is a cargo ship to transport between space settlements. There's Uranus, Miranda, and then an entry capsule here by my colleague, Michelle. So I really appreciate being able to give this talk, since I know most people's interests here are much further away than our solar system, but I'm delighted to share this vision. Thank you very much.
Thank you very much, Jeff. One introductory question, maybe, because could you, one of the reasons why I was interested on that way back is when I realized that there is a finite quantity of helium on Earth, right? Can you comment a bit on that, on how the price rises and the availability to actually do science, because for low temperature physics.
That's a great question. When I was in graduate school at Cornell, my first job was to fix a helium-3 refrigerator that was older than I was. And I did that, but I came to appreciate how precious helium-3 was. So I've had a relationship with helium-3 for the last 40 years, actually, when I added up. And back in the day, that was during the Reagan administration. And it turns out helium-3 is a byproduct of building thermonuclear weapons. And so there was a lot of it back in those days. But since the end of the Cold War, there's been less and less of it. So there's kind of a crisis in low temperature physics, not only for helium-3, but for helium-4, the primary isotope, because the US government used to fill empty oil wells in Oklahoma with extra helium and keep a national helium reserve as a precious resource. And then everybody got all excited about economic rationalization. Like, oh, you just sell all the helium to whoever wants to buy it. And now so they did that. And now there's a real shortage of helium-4 and of helium-3. So that's a problem in cryogenics, low temperature physics. It's really hard to get to 20 millikelvin like I did for my dissertation if you don't have helium-3 and helium-4. So this is partly a solution to that. I mean, the moon's a little bit closer, but the price of helium-3 has gone so high. It's like probably $100,000 a kilogram or something insane like that. And so this has been something I've been thinking about for a long time. So both helium-4 and helium-3, it's probably not economic to transport helium-4 between planets, but the helium-3, if you could burn it in imaginary reactors, would be worth about $3 million a kilogram. So that's probably SpaceX could figure out how to do that. I don't know about NASA. NASA if the moon was covered with rubies the size of chicken eggs, NASA would probably still figure out a way to lose money on it. But I think maybe SpaceX would be able to figure that out. So.
Thank you.
So anyway, thanks for your attention. It was really fun to give you a talk on something that's kind of outside your wheelhouse here.
Thank you.
Astrophysicists.
Thank you, Jeff. I don't know if there is any question now. Andrea?
Yeah, the question related to what you mentioned, I mean, how cost effective would that be? Because the cost of transporting the helium-3 from the other side of the solar system to Earth would be enormous.
The way I look at it is in terms of energy economics. So if you look at, megajoules per kilogram in the helium-3 versus megajoules per kilogram to transport it, it's a really big benefit. Turning that into money is a little bit outside my expertise, but as a physicist, I would say you get 100 times as much energy transporting a kilogram of helium-3 from Uranus to Earth as it would cost to do the transportation. So that's kind of a limited response. It doesn't violate a law of physics to make money on this stuff. So that's why I'm in physics, not business. But yeah, the energy economics works out quite well, including the energy required to extract helium-3 from the atmosphere, then transport it across the solar system. It's a factor of 10 to 30 advantage in terms of energy. So someone smarter than me in business could figure out how to turn that into an economic advantage.
Can helium-3 be produced here on Earth through nuclear reaction?
They're, of course, they've been working on tritium-deuterium fusion for quite some time. There's a group at the University of Wisconsin that is looking at electrostatic confinement approaches to helium-3 deuterium fusion. But it's harder because you have to overcome more electrostatic charge. And so we're still starting out on the helium-3 deuterium fusion plasmas.
So it is harder than mining it on other planets.
It's harder, excuse me?
It is harder to produce helium-3 here on Earth than mining it on other planets.
Yes. Yes, that doesn't mean it's economically viable, but there's almost no helium-3 on Earth except the waste products of thermonuclear warheads and some stuff that leaks out of the mid-ocean ridges from deep in the Earth, but it's a very, very small quantity. One way, that's a good point, because one way to make helium-3 is to make tritium and just wait 12 years. And so you can take lithium, which we all want now for our electric cars, split lithium with a fission reactor, and that makes tritium, and then you wait 12 years for helium-3. But then you have to build these fission reactors, and for some reason people don't like fission reactors. So that's why it's extraterrestrial source. But yeah, you could do it. You could definitely make helium-3 if you make uranium fission reactors to split lithium and then wait 12 years. But that's getting into economics and politics.
So why Saturn and Uranus and not Jupiter?
Jupiter has a hotter atmosphere and a much stronger gravity. And so the hotter atmosphere means that you have to be deeper in the atmosphere, and the stronger gravity means you couldn't build a single stage to orbit reusable nuclear rocket to bring the helium-3 back into space. So
And there is nothing on Mars. I mean, you said that there's something in the moon, right?
yeah, well, there's something in the moon because the solar wind implants it into the lunar regolith. And my understanding is that the Martian atmosphere would block the solar wind from implanting helium-3. So I've not heard anyone talk about helium-3 on Mars. So Elon will have to go elsewhere for his helium-3. Yeah.
Roman?
Just out of curiosity, in this science fiction mining scenario, because you mentioned environmentalists, do you imagine protected nature space?
Well, that's really interesting. I gave a talk to our church about the moon and stewardship and environmentalism. And I didn't talk about Saturn and Uranus, but I talked about how to extend our principles of social justice to outer space. And so if we were to mine the moon for helium-3, after 100 years, there would be large visible scars on the near side of the moon because helium-3 tends to concentrate on the Maria, the dark spots of the moon, especially the Sea of Tranquility. And Fan and Jin's paper from 2007 is really good about that. So I can imagine that, and it's already happened in some sense because the American moon lander Peregrine, which was launched in January, had cremated human remains on board as a commercial venture. And the Navajo Nation of Native Americans said, this was a desecration of the moon. Why are you ignoring our concerns about this? You shouldn't be burying people on the moon. And then as soon as Peregrine was released from its launch vehicle, it failed because a valve broke catastrophically. So I don't think I'd ignore the Indians next time they say this is a really bad idea. So it's very interesting you ask that because Janine was at that talk and I talked about, well, what would be the environmental, spiritual, making space available to all people, but if someone's going to invest money, they need to profit from it. So we're just kind of getting started about it, but it's good to talk about it first, so we don't have some nasty surprises down the road. Good point.
Well, if there are no more questions, let's thank Jeff again.
Thank you. It's your pleasure to be here.